Okay, I'm showing 9 o'clock Mountain, so 10 a.m. Central. I still see people coming in, but it's the top of the hour, so we're going to go ahead and get started. Today, we have a very special guest speaker. We have Tim Marshall speaking to us on the use of EF scale in tornado damage surveys. To give you a little background on Tim Marshall, he is a engineer and meteorologist with Haag Engineering company. Sorry if I didn't pronounce that right. That company is based in Irving, Texas, and he has worked there for the past 38 years. Tim specializes in surveying and assessing building damage in the wake of natural disasters. He was born and raised in the Chicago, Illinois area and became interested in tornadoes when his hometown was struck by an F4 tornado on April 21st, 1967. Tim has a bachelor's degree in meteorology from Northern Illinois University, a Master of Science degree in atmospheric science from Texas Tech University, and a Master's of Science in Civil Engineering also from Texas Tech. He has been a professional engineer since 1989. Tim has written about 100 papers on storms and building damage and has appeared on dozens of radio and television programs. He has served on several committees regarding severe weather and has been involved in upgrading the enhanced Fujita, and Saffir-Simpson damage scales. Tim has participated in Vortex 2, Rotate, and Twirl tornado research projects where he deployed instrumented pods in front of tornadoes. Tim loves to chase storms and has observed more than 300 tornadoes and experienced more than 24 hurricanes. He has presented more than 1,000 lectures on damage survey analysis and storm chasing and has taught a course on damage surveys for more than 20 years at the National Weather Service Training Facility in Kansas City. So Tim, thank you very much for adding us to your thousands of talks. We appreciate you being able to squeeze another one in for us. So with that, I'm going to pass the floor to you, and we look forward to hearing all the knowledge you have to share with us today. So Tim, take it away.
Well, thank you so much for the invite here to speak about one of my favorite topics, which is surveying tornado damage. I, of course, was involved with the Oklahoma tornado back in 1967, and as a 10-year-old child, I was very curious about what this thing comes from the sky that causes such devastation. All it is air and water. I mean, how can air and water do this kind of damage? It just boggles my mind. And I was already into science. I was already taking weather observations. I had every day a sheet that I filled out to take weather observations, and I knew I wanted to study weather for the rest of my life. So it was a chosen field for me. So I went ahead with curiosity and studied tornadoes and tornado damage. And it's been my whole life. So I've done this since the 60s, was on my first formal survey in 1976, and have surveyed hundreds of tornadoes and destruction and many thousands of buildings. So I got involved with this thing called the EF scale. I'm going to talk about that today. First of all, I want to see how I can advance this. Anybody have any suggestions how I can advance the?
It should just be your regular slides. There you go.
Okay. Yeah, maybe it's a little slow to respond here. Just to give you a background, yeah, everybody's familiar with Fujita scale, I presume. Everybody is familiar that it was developed in 1971 by Dr. Fujita. He basically saw 3 levels of damage in his short term at that time in surveying damage. He figured there was a weaker tornado and there was a stronger tornado, so there's your 5. Okay, so that's where his empirically derived F scale came from, and the wind speeds were another matter we'll talk about a little bit. But a meeting was held in March of 2001 in Grapevine, and 20 participants attended. We developed a list of damage indicators that is different building types and then degrees of damage for those building types. And the group agreed to preserve the historical damage scale and keep the we call it 6 numbers, but it's actually, from 0 to 5. And then 6 experts were selected to develop the wind speed part of it, and that one of those was me, so I was really happy about that. As you know, there are 28 damage indicators, and with one at farms and barns, and then all the way down to trees. And I will let you know that we are going to be changing a lot of this in the future. So what's a degree of damage? Well, each building has several degrees of damage, as you know, and we know that buildings can be missed. We know that buildings can be destroyed, and we know that there's actually an increasing order of damage as you go from no damage to total destruction. So we developed various DODs, or damage degrees of damage, for each building type. And it's a function of wind speed. The wind speed we're talking about here is a 3-second gust at 10 meters above the ground. And the reason we do that is because building codes deal with 3-second wind design at 10 meters above the ground in the US. So this way we can match that. The old Fujita scale was not based on 3-second gusts at 10 meters. It was based on a 1/4 mile fastest mile back in those days, which is similar to the 3-second, but not exact. And then we established a range of failure wind speeds for each DOD. It was empirically derived, so it's a process known as expert elicitation. You've all seen this. This is for residences. It's the most common DI out there. And the way the document, the EF scale document, was arranged, and it's about 111 pages, is it starts out with the DI, in this case 1 and 2 family residences. It has bullet points. What's your typical construction, very general. And then it has this table here, which has the degree of damage going from 1 to 10 with a descriptor there about what we're talking about. And then it has actually 3 ranges here. EXP is an expected wind, LB for lower bound, EUB for upper bound, and that these numbers were derived from the 6 individuals, including myself, to try to come up with a range. And you see that they're into the mile per hour, and of course it's not that accurate. We don't mean to be that accurate. The updated EF scale, as you will see, will be rounding things up to the nearest 5 miles an hour, because we don't want to have this level of scientific precision, because there really isn't that level of scientific precision. The damage description is a bit general, like number 1, threshold of visible damage. What does that really mean? Okay, well, in the updated EF scale that will be coming out, it'll have a lot more in the way of describing what that means. And then it has the 20% there, the loss of roof covering material, less than 20%. And then that was just a number that was chosen. And we're going to actually do 25% increments in the new updated EF scale, and all the way on down. And as you can see, it's really general. I mean, entire house shifts off, foundation number 5. How much of the house is shifting? Does it matter? Yeah, it does. Number 7, exterior walls collapsed. How many walls we're talking about? So it's very general, and that makes for then some departures from the expected value, and we get sometimes some wild and crazy numbers. So hopefully the updated EF scale will tone that down a bit. So expected, what does that mean? It means it's built in accordance with the local building code, typically in the center of the US. Now, the standard is about 90 miles per hour, 3-second gust at 10 meters. That's about the standard minimum wind. That number's been changed to 115 as far as an ultimate wind in the newer codes, but that still means a 90 mile per hour, 3-second gust is what it does. So it's not much of a change at all in the design, and it hasn't been much of a change for many years. So 90 mile per hour, 3-second gust is what I think of as the standard local building code in the center US. Now, an upper bound means that building is built above code, that there's been actually things done to the building to help it resist wind. For example, adding straps on the roof and wall plates to tie down your house, anchoring it down properly. Those things can make a house more wind resistant or a building more wind resistant. Also, buildings now in hurricane prone zones can be built better. And I say can be, not always the case. But Florida has their own building code, which is much stronger than most of the other building codes. So at Florida, you should have a better built building, but that's not necessarily the case, as we've seen. It's usually for the newer construction and not for the older. Lower bound is, and there's a lot of these, missing, deteriorated, critical connections. And I'm talking about critical connections. How do you recognize that something is a critical connection? A board may not be nailed together, but does it really matter? Well, we'll talk about that a little bit here in this session here. And then the ABCs of engineering: anchors, braces, and connections. Obviously, the type of anchor, brace, or connection, how good a condition it is, that's the key. Sometimes things are not anchored, and sometimes things are poorly anchored, or attempts were made to anchor it but didn't really anchor anything. So we see that occasionally in engineered buildings, but we see it very common in houses and things that are not engineered. So if you compare the two, they are a little different scales. The old Fujita scale, quarter-mile wind, adjusted for 3-second, is pretty close at the lower ranges and the lower EF 0, 1s, and 2s. But by the time you get the 3s, 4s, and 5s, you notice a substantial departure between the EF scale winds and the Fujita scale winds. Now, why is that? Well, it turns out Fujita took the difference between the Beaufort 12 and the Mach 1 scale, which is an aviation scale, Beaufort's nautical mariner scale. He connected the two, and then he divided it into 12 unequal increments, and that's where he got his wind speed ranges. Well, that turns out to be a pretty far out and left field way to do things, which Fujita was notable for. And it just didn't match what the engineering science said about what wind speeds were. And so it doesn't take a 261 mile an hour wind to knock down a house and wipe it away. Engineers said that could be done at 200, and sometimes quite a bit lower than that if the building is not anchored properly. So there was this adjustment made to the wind speed ranges in the EF scale. So kind of summarizing it up, the EF scale uses the concept of wind speed damage correlation rather than obtaining the wind speeds from the Mach 1 Beaufort 12, kind of dividing it in 12 increment thing. The degree of damage is assigned to a damage indicator. The wind speed ranges are assigned to each degree of damage, but they're not, of course, without their own errors, and we'll talk about that. And of course, the tornado is still assigned the EF rating by the worst damage in the path, the same with the EF scale. So here's some positive and negatives. I mean, the EF scale provides wind speeds necessary to cause damage as determined by the experts there, and there are exceptions. It's subjective. Still, errors can be substantial. EF scale, though, is applied to more than one building type. The original F scale was for houses and not really for other types of buildings. The EF scale is more complicated because we're dealing with more buildings and building types and has this degree of damage thing. And it has limited use because how we build buildings in the US is not how they build them in Europe. So there are limitations with trying to expand this to the world. We're looking into that. Canada has their own EF scale, so does Japan. Europe, it likes the old F scale, and the UK likes the Toro scale. So There are still variations out there, and we've looked at those, and hopefully we'll get some consensus. The Canadian EF scale is pretty darn close to what the US EF scale is, and so in Japan. So there are some common ground here. I think the key here is how do you address, recognize these fatal flaws in these buildings, these critical connections. And what I mean by a critical connection is when it fails, then you get catastrophic damage to the building. That's what a fatal or critical connection is, and recognizing that. That's a key. It comes with experience. You have to do that, and that's just takes more surveys. Get out there, take a look at it. How do you address tornadoes in open country? Damage to vegetation, irrigation systems, road pavement. There's so many other non-DIs out there, and then there's some times where you don't even have a DI. So these are big issues because a lot of tornadoes occur in open country, don't hit anything. And then how to address these other scales in these other countries. What changes can we make to the EF scale, and how is this done in the future? So all of these are great questions. They can take hours to go through discussions, but they're out there. We know it. We know that this is not a end-all work, that it will take some time. I'm sticking again.
Not sure why it's slow to update sometimes.
Yeah, it's just something to do with buffering or something.
Interesting. I'm not totally sure.
Okay. Well, I think I'll hand it back to you, and we'll see if I can restart this.
Okay. Okay. All right. I guess while we're waiting, are there any questions out there so far? If you do have questions, feel free to put them into the question box, and I can either ask those as we go along, or we do have a planned question and answer time frame at the end of the webinar. Tim, do you have your PowerPoint presentation in autosave mode? Because that may be potentially what's causing it to hang up.
I might. No, autosave is off. It's showing as off.
Okay.
Okay. Let me see if we can start this here where we go back to it. I may have to go back and forth occasionally.
Okay. Okay. I see a new slide there.
All right. So now big drum roll here for you. We have been working on this project of updating the EF scale. It is a massive effort. It has taken the last 7 years of my life and all my free time to try to work on this project. The American Society of Civil Engineers got together a group of about, well, it started out with about 20 or 30 people, and now it's probably 80 people, of trying to make the EF scale a standard. And that takes quite a bit to do. And a standard is actually a law. So it's trying to make this into some sort of law like a building code. And so this project began in 2015. And we've gathered a lot of information since the initial EF scale came out. The initial meeting was 2001. The first document was in 2004. The second document was 2006. That document was 111 pages. The current document I'm working with on is 300 pages after 7 years of work, and we have many more years apparently to go on this, unfortunately. And so there's a lot here. And just to give you a heads up about what this is going to look like. Yes. Okay.
Okay.
Let's go on to the next slide.
Hey. All right, everybody. We're back and moving forward. So, Tim, it's all yours again.
So if you recall what the wood frame residences in the 2006 EF scale looked like, it had some bullets on it, kind of general. Well, here are the bullets for the new updated version, which you can see there's quite a bit. Well, it still has the general description, but now we're talking about those 3 columns in there. What's typical, what's stronger than weaker. And granted, this is a lot of bullets here. And then the reason we put a lot of bullets here is because of the wood frame residences. The other DIs don't have this many, but this just kind of goes into detail quite a bit about what you would expect to see with something built normally, with something that's weak, with something that's built stronger. Next slide. Of course, I'm not going to go through all of it. So let's go to the next slide. Unless it's sticking on you too.
Yeah, I'm trying. I get the spinning wheel.
Yeah, it's like a buffering issue, where it just seems to be really slow. I don't know if this has happened to anybody else and any other, but it seems, okay, well, there we are. We've got a table here. Again,
Okay.
remember the table in the 2006 EF scale, it kind of was very general, threshold of visible damage, and then it just ended. Well, here we say such as, broken windows, doors, skylights, toppling a poorly attached chimney, bent TV antenna, loss of chimney cap. So giving you some idea about what that means. So it's a lot more information. Now the wind speeds are pretty much the same in all of these. We just rounded them up to 5 miles an hour. So we're not dealing with single digits to give the false impression that there's this scientific precision out there. There isn't. We were even debating to do it per every 10 miles an hour, but I guess the consensus was every 5. And then if you go to like DOD 2, you see that it says minor loss of roof and wall coverings, and it says less than 25% of that. So, and then you'll see down at the 3, it goes 25 to 50. And then for 4, it's 50 to 75. And for 5, it's greater than 75. So you can see that it's giving you a lot more detail, separating it in 25% increments like that. And it still has, for the typical resistance, a house that's blown away with the debris, as long as it's built properly, is 200, which is 5, EF5. Next slide, if you can get to the next slide. Let's see if we get the spinning wheel phenomenon that we have been getting. All right. So we have a commentary. This is new in the standard. This is a reference commentary. So this is like a paper. So every DI, and there's 28 DIs, is going to have a commentary that's referenced, almost like its own paper. And that's based off of the fact that we've had, over the last 20 years, many tornado damage surveys. A lot more information has been gathered. You all have the DAT tool, or at least some of you do, and that's been very helpful because I get those photos as well. And it's very good to have this amount of information and references. FEMA and NIST both have gotten into the damage survey, and then they've done published reports on surveys, so that's good. The updated EF scale is also going to have these photos in it. Now, I'm a photo rat. I take tons of photos, and over the last 40 or so years, I have accumulated in the neighborhood of probably 30,000 images of various damaged buildings, and trying to sort through those to come up with something that'll be in the standard has been a real task to do, but we've done that. So the next slide, if we can get to the next slide. So let's go through some of this. And this is really what the remainder of the talk's going to be, is going to go through each of these DIs, just briefly kind of tell you what's typical. For barns, that's DI1, a typical construction is, it is a metal-clad wood building. Just because it has metal does not make it a metal building system. A metal building system has steel members all throughout. So it has a steel roof, steel columns. That's a metal building system. I looked through some of the DATs and I see some of those mischaracterized as metal building systems. These are not metal building systems. The typical construction for barns is that you have wood posts. They're either in a foundation or in the dirt. They have maybe a Y brace along the perimeter beam, but there's no cross bracing. The roof has no solid decking. It's just open like that. And the trusses have minimal bridging, that is, to go across from one truss to another. So this is kind of the minimal. Sometimes you'll have straps, sometimes you won't. But it's the big weak link, of course, is how it's attached to the ground. And you can see that's a pretty weak link there. There may be a footing in there that they're embedded into, but wood against soil, you know what happens over time, don't you? It just rots. Next slide, if we can get there. All right, on the left is something a little more formidable. You have a double perimeter beam with nice straps. You have a solid sheathing on the decking. You have not only the Y brace, but you have another brace that comes in to stabilize the trusses. So that's a better built barn right there. On the right, that's a below normal barn. You don't see any Y bracing there. There is no bracing whatsoever. That perimeter beam is really like just a 2x, or if it's that, a 2x. It could even be like a 1x3 or something. It's not a very good barn at all in terms of structure. So just to give you some idea of what's kind of normal, what's kind of a little beefier, what's kind of below the normal. Next slide. So we'll see if we can, yeah, all right. So now this is going to be an interactive talk where I'm going to actually involve you all in this. Here we have a barn that is destroyed on the left. We have the posts, as you can see, snapped off at the ground level. The posts are rotted, some were pulled out. You go over to the small barns and farm building table. Where would you go here in terms of this? I think we can all pretty much agree it's DOD 8 for just total destruction of the building. Expected wind is 112, lower bound wind is 94, upper bound wind is 131. So where do you think that's going to be? You think it's expected 112? You think this is lower bound? You think it's upper bound? And if you go to the next slide, you'll get the answer. Okay, I figured lower bound because of the fact that the posts were rotted. Okay, so next slide. Now, wood frame residences, as we know, this runs the whole gamut in terms of from poorly built all the way to well built. And it depends where you are in the country, of course. It depends what kind of foundation you have. The three big features that distinguish a better built home would be where you're using straps to anchor down the roof to the walls, where you use solid sheathing to make a box, and where you anchor bolt the bottom wall plate to the slab. Those are the three big connectors for a house. This is taken in Norman and Moore, Oklahoma. You can see on the left, green board or silver board. This is a cardboard that's used. Has no structural ability whatsoever. It is not a box. It does not lock in the frame. So this type of construction will meet local building code, which is 90 mph, but it certainly is not a better built home. The one on the right is a better built home. It's strapped down, which you can't see, but there are straps there, bolted down, and also has the solid sheathing around it. So that locks in the frame that's the way to do it. It is above code slightly, but in Moore has a higher code, and that's what they require now in Moore, is to build it better like that. Next slide. Building codes, what are they? Well, they are what municipalities can adopt, and then houses are built and other buildings are built in accordance with those. And interestingly enough, your big box building or your Home Depot, your Walmarts, there you go to the same code as your house. And currently we have what's called a 115 ultimate design in the center of the US, which is like equivalent to a 90-mile-an-hour 3-second gust. The higher codes are for the coastal areas because of hurricanes. But just because there's a house or a building being built there does not necessarily mean it's a better building, but it should be, especially in the today's market. But some of these counties you see don't have building officials, and so don't have the enforcement. The buildings that fall under this are residences, but not manufactured homes. Manufactured homes do not fall under this building code, and we'll talk about that. It's a different set of rules. Next slide. Those of you who have heard me talk many, many times, on the left is a detailed cross-section of how conventional anchoring is done, what's normal. That is, you have a wall stud, the X there is the bottom plate, and then you have straight nails, 2 nails coming in to attach that. Then a J-bolt that goes into the concrete slab. It looks like a J. There is a nut and a washer, so it's a 3-piece anchoring system. That is the conventional way, the minimal way to attach walls to slabs. F indicates the failure locations we see typically with houses being pulled apart. Usually it's a wall failure and the bolted plate stays. On the right, we've got these below normal substitutes and straps, shot pin, and a cut nail. Now, most municipalities, when they look at this, they issue variances. And the reason they issue a variance that you can depart from a building code is because they get a lot of complaints. In order to put a J-bolt in, that slab has got to be freshly poured. You can't put a J-bolt in after the slab is solidified. Well, that's a different contractor. The contractor that frames up the house and the contractor that pours the slab are two different disciplines. They got to coordinate with each other then where the J-bolts need to go, and that rarely ever happens. And so we get bolts that are in doorways, we get bolts that are outside the plate, and we get all kinds of bolts that are too deep, bolts that are too shallow. It's just all kinds of problems with putting J-bolts in when the two trades don't talk to each other. So municipalities say, well, why don't you put a shot pin in where you shoot it down a dowel into the concrete slab? Well, when that's done, it fractures the slab. Cut nails are not allowed in any building code, and no municipality that I know of allows them around the perimeter. They will allow them in the field or in the interior walls, but they won't allow them around the perimeter. But that's tough to do. Have you ever tried to nail in the concrete? Really tough thing to do. But all those don't provide very good resistances at all. And the best way to do is to put in a hurricane clip at the top, solid sheathing, and then bolt it at the bottom. Next slide. So I'll give you a little difference between what's normal on the left. Toe nailing is also allowed. There's a shot pin there that will meet building code. On the right, having a nice J-bolt there, wider plate there, so 2x6. Having a nice connector plate like that, above normal or above code. Next slide. At the roof level on the left, typical toenail of a rafter under the top plate. That's we'll meet code. On the right, above code, showing how you can put in these hurricane clips and tie them into both top plates. Next slide. All right, so now to our question for you all. Here we have a conventionally built house. This is in Richardson, Texas, from the tornado I think a year or two ago. This was a toenail connection, so it will meet code. Now go over to the right. Where would you put this here? Come down. Looks like DOD 6 says large sections of the roof structure removed, but walls remain standing. That looks good. Given that it's just a typical built, it's not poorly built, it's just typical built. The next slide will show you what I think is the answer. So we'd have about 122 there for that. Okay. Next slide. If we can get to, yeah. All right, here we are. Now, this is another example. This is a poorly built home. This house was literally 2 stories, okay? Complete collapse, pile of debris. Look at the surroundings. Other trees look okay, pretty much. Other houses look okay. And this house is a complete collapse. The first floors were cut nailed around the perimeter. And you can see that in the inset photographs. On the left, there's a cut nail. On the right, there's the divot. Just like taking out a carpet tack strip, isn't it? When you go ahead and do that, pop off that little clear cover. So here we have a house that fell and is totally destroyed. So where would you go here? If you look down the table, DOD 9 has all walls down, but this is a poorly built house. Next slide. Show you the answer. There you go. Lower bound, 142, probably didn't take that. All right, the wood frame residence here, another poorly built house. We can see the roof is gone. We can see that it's not anchored at all. It's on these hollow blocks. And so it gets, it's going to be a lower bound somewhere, right? But we have 2 types of DODs here. We have the roof that is gone, and which is a conventional roof. Unfortunately, though, that it had poor connectors up top as well as the foundation. It had some rotting. It had some termites. Those things make a difference. So here you go down. It'll probably be in the lower bound range. But now we have 2 things here. We have a roof gone, and we have the house is slid. So where do you go with that? Well, it's DOD 5, DOD 6-ish, I would think. Okay, next slide. See where that ends up. So you can see they're pretty much close. To remove the roof and to remove the house is about the same, and that's about right. That's what it takes. Next slide. Manufactured homes, totally different animal than a regular built house, and a totally different kind of standard to deal with, and we'll talk about that. Homes that are not attached properly or not attached, as these cases, you don't see any straps here, nothing around the beams. They're obviously below normal, and wind can take these over pretty low wind speeds. Next slide. This is not an ASCE map you're seeing on the left. This is a HUD map. HUD has its own map and its own wind requirements, and they range a lot lower than the ASCE maps, especially for a hurricane zone. So you go from basically 70 to about 110 is on these zones here. What's normal construction is in the upper right. Normal should be a strap down frame, and that has an auger anchor that's properly sized in its depth. It has a stabilizer plate, which we'll talk about what that is. That's a plate that it bears up against when it's driven in on an angle. In the above, in the higher zones, which are zones 2 and 3, you have a frame tie as well as an over-the-top tie. And that's 2 different ties that are anchored it down also with the stabilizer plate. Next slide. So the strapping looks like this for the better built. If you have an auger anchor, you have a stabilizing plate, which is about a 1 foot wide plate that actually is driven into the soil, and it is to bear that rod of the auger anchor. And then you have the double strap, the strap that goes over the I-beam underneath, and the strap that connects the home down. The different sizes depend on your soil types. If you're in sandy soil, like in Naples, Florida, you're going to need that longest anchor, probably something 48 to 60-inch long anchor. And that's what you need in the soft soil to get the proper pullout. Next slide. Go into a little bit of detail on these because you deal a lot with manufactured homes. You first install the auger anchor on an angle. That's, of course, just away from the home itself. Then you install the stabilizer plate. Then you tighten up with the strap, and then it bends that rod so it engages that rod against the plate, and the anchor head is level or very close to the ground. Should not stick above the ground. Next slide. Now, I know you don't have soil test probe kits, but in order to know which pullout strengths you have, you need to have a soil sample, or you need to pull out a auger anchor and to see what strength it is. Now, I know we don't do that. We just have to kind of guess whether the auger anchor was long enough or not. Next slide. Proper tensioning is important, making sure that it's not loose, that it's tight. You will be able to tell if the home was rocking around. I'll show you how to do that. Next slide. The frame tie goes over the top and around right over it again. And you can see examples of the top of the auger anchor, the anchor head, and the stabilizer plate on the bottom. Next slide. In many instances, the wrong anchor is used on a home. This is what's called a rock anchor. This was in Pitcher, Oklahoma. Almost all the homes I looked at had wrong anchors on. And I'll show you a close-up in the next slide. I'm holding in my hand on the right what's called a rock anchor. This is supposed to go into rock. It has these tubular, a couple of tubular welded pieces of steel onto the rod, and then you cross it in the middle there with these anchor rods. That's good for rock, but it's not allowed for soft soil, and all of the homes I looked at in Pitcher, Oklahoma were on soft soil. So obviously this just slides right out. The home is in essence not anchored, and of course you saw what happened to the home, and many of the homes are just flying around. Next slide. So even though it's anchored, it's the wrong anchor. Here we had loose straps. You can look at the strap, you can see the wear mark on the end of it. That tells you that this thing was moving around back and forth several times. You can see the different layers of wearing there as it's rocking back and forth until it finally broke. Next slide. And then a big negative for all these galvanized steel straps is the environment. Down in Florida, I've looked at so many homes down there that the straps were done properly. However, this was done 10, 15, 20 years ago, and they're no longer held down. Everything is completely corroded. The steel there is covered with a zinc coating, which protects it for a little while, but the zinc is water soluble and will come off, and now you have steel in soil and it just corrodes away. Next slide. So I've learned over the years that the better built manufactured homes, the boxes are done really well. I've gone to plants and seen them. So it's just a matter of how well is it attached. And here, after Irma and 100 miles an hour, Laura and 130, and Lake Charles, I saw that homes that had the double attachments, that had the attachments of the frame and the attachments over the top, if they were done right, the home survived. Even though some of them had some kind of issues with roofing and siding, that's to be expected. These boxes stay if they're done right, if they're anchored right. Next slide. So now here we go with our interactive test. We've got a single wide that has slid off its foundation. It also has its entire roof has been damaged. So we come over to the table here. This is conventional built. There's nothing that's, I would say, that was too poor about it. See the surrounding damage. So I would say this is kind of an expected column. You come down here though, now we've got two things going on. We've got on, see, complete, we've got number 3, unit slides off block piers but remains upright, okay. Number 4, complete uplift of roof, most walls remain standing. Well, we don't have any real wall damage here, but we've got, really the roof has been completely uplifted. So the next slide tells us an answer. They're somewhere, I think 87, 89 miles an hour. Looking at. Next slide. Apartments and condos, just give you some example here. We have a roof gone, 2-story, brick building, wood. It was conventionally attached, no straps or anything. Next slide. Gives you an uplift or collapse of the roof structure, leaving most walls standing. Well, again, all walls standing. You may come down a little bit and say, oh, it's probably closer to 130 or 125 because we don't have really any wall damage here. Next slide. This horrible construction here, but you know that tornado was really very powerful here at this time. Next slide. Still top 2 stories gone, 3-story. Yep. Next slide. Motel, top gone here in terms of the roof, some exterior walls, conventional construction, come down here, collapse of top story exterior walls. Well, not quite. Uplift of collapse of roof structurally, most walls standing, number 6. Next slide. So there we are. You see how this is working? And this is what I do. And hopefully it's kind of the same thing that you guys have been doing out there in the field. Next slide. Small retails, buildings, looks like a McDo here. This is a McDo. And we have on the small retail building, we have loss of roof covering. Don't know if they're about the decking and that unless we get up there. So it's going to be kind of a big question mark there. We do have some windows maybe that were broken. We don't know that until we go around the whole building. So you got to walk around the whole building. Next slide. So we got some roof covering damage, uplift or collapse of entire roof structure. We don't know that until we get in there. In this case, there wasn't that. So it was actually closer to DOD 4 here. Next slide. Here's a Walgreens, small retail building, complete or almost all complete collapse of the roof. And this is in Joplin. Conventional construction. So we have uplift or collapse of entire roof structure, or almost entire roof structure. 6, 7 didn't really happen. Next slide. So, got to walk around the building somewhere in maybe between there. Next slide. Looking at the strip mall, a lot of damage here. This is one of the more severe damaged strip malls I've seen here in the Dallas tornado. This here had the roof gone. The walls were leaning, as you can see here. It didn't really topple. So we've come down here. We've got, DOD 7, uplift or collapse of entire roof structure. DOD 8, collapse of exterior walls, closely spaced interior walls remain standing. So maybe somewhere in between. Let's see what our next slide is. Uplift, collapse of entire structure. Okay, if we could get the walls to collapse, I suppose we go up a little higher. Next slide. Large shopping mall. Looked at this mall in Jonesboro last year. Several sections collapsed in this thing. Well, when I started looking at this, I'm sitting there, a large shopping mall you would think would be built to code, at least to code. But we're kind of, in the rural area in a way. Arkansas. We'll see what happens. Next slide. Looking at the collapsing of these walls, they were done with steel studs. Now, we're talking about 20-foot tall walls here. And looking at the base of that wall, I'm seeing very little attachment. If anything, there were maybe a few nails to the right of the tape measure. You can see some rusty nails there. No bolts used at all. This thing was horribly built, and it had immense damage to it. Next slide. So even the two-story here, it was a Dillard's. Poor attachments. No real attachments to the steel structure up there. This was just kind of freestanding walls. So we have a large shopping mall. We've got, well, the roof structure is not uplifted or collapsed, but we do have exterior walls and top story collapse. So it's going to be interesting there, where we want to pick this. Next slide. Somewhere between 108 and 124, I think, there in the lower bound because of the poor building connections there. And so I think the bottom line is it doesn't matter how big the building is. It doesn't really matter where it's at in the country. Even in the hurricane-prone zones, you're going to see poorly connected kinds of roofs and walls in all kinds of buildings, even the ones you would think being engineered. Next slide. Large isolated retail building. Looked at a bunch of these. This one here is one in Dallas that had some wall collapse. Most of the walls remained. Had a lot of roof damage, you can see. Next slide. So just the front few panels collapsed inward there, right near the entrance where there's a lot of openings there. So looking at the table here for large isolated retail buildings, we've got looking at long spans collapse downward, not really, but there is uplift and removal of the roof covering, but not the structure. So it's going to be lower than that. Next slide. So I would say some long roof spans collapse downward would be it. Again, we don't say how much there. The new and updated EF scale will have more description in it about what percentage, but here I felt somewhere around 122 here. There's a pole, as you see next to here, and that's an actual electrical transmission line. And you can go to the ETL DI and look at that, because that wasn't damaged, so that will give you an upper bound on that. And that's one of the things you can do is do kind of a bracketing where what's damaged gives you one number and what's not damaged gives you another number. Next slide. This is the Home Depot in Joplin I looked at. As you can see, practically all wall panels are down. The entire roof system was removed and deposited in the field. This was a violent tornado that happened in Joplin that unfortunately led to many fatalities here in this Home Depot. Next slide. The complete destruction of it, 173. Next slide. Automobile showrooms. This was high-end vehicle dealership. They had lots of glass, so you can see inside their building from basically the floor to the ceiling, all glass, except on the back wall, which had the CMU. And we'll take a look and see how well that CMU is attached. Next slide. On the left is the attachment at the roof level. You can see it has a little J kind of hook there that goes into the bond beam. and that was its attachment there. You can see the hanging CMU that's there. Really wasn't much in the way of, maybe that cell had some grout in it, but you can see it fell away. At the bottom, there's no rebar of any kind, no horizontal, no vertical rebar, no foundation rebar, no wall rebar. It's just, again, a freestanding CMU wall. So that would be poor construction in my book, and would have to be in the lower bound. When you look down the column here and you're looking at, exterior wall collapsed, 7, something like that. Next slide. Okay, lower bound at 7. Next slide. Elementary schools. Again, you would think that schools should be built better than anything else, but they're not. This is a wall that fell out in an elementary school in the south of Dallas here. I went out and looked at this, and it was not attached at all to any of the steel framing. And the only thing it was attached to was the foundation. Next slide. And how it was attached was abysmal. Some nails, and you can see the depth of that nail, maybe a ½ inch into concrete, leaving divots on the right in the concrete. Horrible, absolutely horrible construction. And as it turned out, they had to come in and replace all of the walls in this school because they were not built to code whatsoever. The next slide. And here's the closer view of the foundation. You see a little divot like you would when you're removing a carpet tack strip. If you've ever done that, just bring off a piece of it, like spoil off the top of it. So you go over to the DI-15 here, your table, you come on down and you see, okay, we've got collapse of a non-bearing wall, but it's horribly attached. So it'd be in the lower bound. Next slide. And yeah, it had some roof covering damage as well. So you could take the highest. I normally just take the highest number there if I have some roof damage and I have some wall damage. Next slide. Another elementary school I looked at here in the Dallas area. This one, pretty heavy damage to this school. Took the roof off, decking, a lot of window damage. On the right, shows you ground view of it. Next slide. But the basketball stops did good. Interesting. So the roof is gone on this thing. We come down over on the elementary school. It was properly attached to the code. We're looking at uplift, removal of roof decking, greater than 20% for sure. Damage or loss of wall cladding, uplift or collapse of the roof structure. So you just walk down there. Next slide. And we get to something about 125. Next slide. Another elementary school. This one is in Joplin. And we've got complete collapse of the school. We've got walls that are concrete masonry with brick cladding. There's a look like a fill in between those two. There is no rebar whatsoever going from the foundation to the wall, or no wall rebar at all. So this school was horribly built in Joplin. Next slide. Looking at the roof level, the trusses, they had welded plates with these kind of bent metal pieces that fit into a bond beam. On the left, you can actually see the bond beam lying there all in a row right underneath that truss. On the right, just shows you the close-up view. Nice clean connection, nice broke right through. That's a minimal attachment. Next slide. On the left, actually the weld was so poor that the plate came away from the truss, and the plate is now embedded in this kind of slopped together mortar grouted bond beam. So on the right, we have an elementary school. We have total destruction of it, but it's just in a very poorly built school. Next slide. So I probably should have shifted that over to 152. Next slide. A high school. This is in Greensburg, Kansas. Looked at this. This was a 3-story school, now 2-story. One of the most severe school damages I've seen. On the right, a 2-story wing of this school. That's all that's left. Closer view on the next slide. We have this hinge line, which is where the window array is. That's a weak point of the building, but it's conventionally built. We have 3 thicknesses of masonry here. We have a brick over a clay block over another clay block, the triple thick unreinforced masonry. It's still minimal construction, but there's nothing too seriously wrong with it, as just Mother Nature takes advantage of the building that has weak points in it. Now, next slide. Complete destruction, 192. It's actually closer to 200 EF5 damage. We bumped these up a little bit in the newer EF scale. Next slide. This is a 2-story office building in Richardson, Texas. I looked at. The structure did fine. The only thing was the windows broke because of flying debris and wind pressure, and then it went through the building and blew out the back side of the building as well. So it was a big wind tunnel. Looking at the DI-17 on the right table, we've got damage going to DOD-4. You have to get up on the roof and look at that, or have a drone. Again, I'm convinced that drones are the key for damage surveys in the future. Yeah, especially you have to have one to look at the roof or get some sort of aerial image. Next slide. Yeah. Expected 101, DOD-4. Next slide. This is a low-rise office building, 3 stories. Glass is gone, part of the roof is gone. This is in Dallas. Looked at this, looking down, we've got DOD-5, uplift of lightweight roof structure. Looks like that could be it. Next slide. Oh, okay, glad I'm right. Next slide. This is a mid-rise building, the Cash America building in Fort Worth I looked at. We've got loss of glass here, and also they have these travertine columns. They're clad columns. You call them a curtain wall. These are sitting up here attached to steel framing. Also have on the right some roof damage, decking removed here. Not a great deal of it, but some of it. Next slide. Looking at how the travertine was attached, there was rebar welded to the steel studs. You see a lot of rust there, a lot of water was getting in. The travertine, basically, they slopped a little bit of mortar on that thing and tied it to the rebar with little twist ties. You can see the twisty tie configuration on the right. Next slide. Not the best, but that is what they can do to meet code. So here, looking at mid-rise buildings coming on down, DODs, let's see, 6, we had some of that. DOD 7, we had some of that. 8, well, it says uplift or collapse of roof structure. Well, not so much the structure, covering and some decking, but not the structure. Next slide. So, so maybe somewhere in between. Next slide. And the big boys, the high rises. This one in Fort Worth, lots of glass damage, lots of flying debris. Debris came from other rooftops, other buildings. It hit this 35-story building. And of course, rocks break glass. What do you know? Next slide. So we've got damage to the glass, the spandrel units, maybe some of the, well, I don't see too much in the way of curtain wall damage. So next slide. Here we've got broken glass in exterior walls at first and second floors, broken glass in entryways. Well, there's a lot more to that, so I probably would bump that up to something. Also, we don't know what the roof material looks like. It could be as high as 143 DOD 7 if we could take a look at the roof. So some of these descriptors don't go far enough, and you got to use your judgment to try to maybe move this up or down accordingly. Next slide. All right, institutional buildings, hospital here with heavy double T roofs. They were not anchored, but they were just sitting up there because of gravity load. Next slide. Heavy building. So here we've got the institutional building, come down, DOD, looks like 8 uplift to precast concrete roof slabs. It was built conventionally. Next slide. That would be 142. Okay, next slide. Moving right along. Metal building systems. Metal buildings do have a tendency to deteriorate over time, and this one here lost end wall. One wall blows in, the other wall blows out. That's typically what happens. The frame was okay, but the studs here were completely corroded, at least in one part of the building. Next slide. We've got the entire wall here laying down, and we've got, again, no anchor bolts, but if you look closely on the right, little nails around the perimeter, and that's all it is, tacked into the concrete. This is poorly built. This is not going to be much in the way of resistance, especially since it wasn't even tied in at the top. Another freestanding wall. Next slide. Look at close up there. That's all you get in terms of the depth into the concrete. Not my idea of fun. So over on the right, metal building systems, we do have metal roof or wall panels pulled from building. Yeah, next slide. 78. Lower bound. Next slide. Gas station canopies. Oh, we've got some fascia that's gone, but the structure did okay. Multiple columns did okay here. Looking over on the right, coming on down, DOD2, fascia material blown away from canopy. It's expected. Next slide. There you go. Next slide. Warehouse buildings, typically masonry, heavy timber. Here we have a non-load bearing wall that has collapsed. The roof still is fine in terms of not damaged. You can see the orientation of the open web steel joist if you look carefully. So this was an end wall failure. If you go over to the table and come on down, you're looking at DOD5 here. This is a non-bearing exterior wall collapse, and that's built as minimal to the code as you get. Next slide. So non-bearing wall 114. Next slide. Electrical transmission lines. Here we have a single wood pole. It's snapped off at the bottom. If you take a look, it's rotted as can be. So I'm looking at this. I come over DOD4, a broken wood pole. It's expected would be 118, but it's rotted, so I'm going to probably drop it down to 98 there. DOD4 lower bound. Next slide. And probably doesn't even take that to knock that pole over. Next slide. Freestanding tower, number 25, that down here. This one's easy. Collapsed microwave tower, expected 136, right? DOD3. Next slide. All right, next slide. Freestanding pole, light poles here. This is, well, it's a bent pole. One could argue it's collapsed because it just hung up on the wire. Expected 102 to 118. Next slide. In this case, maybe 102. Wouldn't argue to go to 118 either. Next slide. Freestanding pole again. We've got a couple of them, both in the same category. We've got a light pole that's bent. We've got a traffic signal pole that's also bent. So next slide. That's a 102. Next slide. So we've gone through the ones without the trees in them. And trees is going to be a new DI in terms of how we're going to look at that in the upcoming EF scale. But what do we do with non-DIs? Well, it turns out there's an effort being made to try to get vehicles into the next EF scale update. This is going to take some doing because vehicles, as you know, come in various sizes, shapes, whether they're moving or not, the angle of attack of wind. Oh my gosh, there's so many things that go into vehicles. And then they're so susceptible to small, short changes of winds. Like you could get vertical velocities on some of these tornadoes that could just loft these things. So there's a lot of debate going on with whether vehicles should be a DI or not. If they are going to be a DI, it's going to be a wide range. It's not going to be plus or minus 20%. It'll be larger than that. Next slide. Billboards. Should we include billboards? I think it's possible. Again, different configurations. There's billboards made of wood. Oh, I like this one. This one comes from Dallas and it says on the left, give it a whirl. And it did. It got a whirl all right. Twisted around and was bent. There's a lot of information that we need to gather on billboards before we can make them a DI. Again, we've been concentrating so many years on structures and buildings, we're not billboards. So definitely look at these other things, definitely take photos, load them in the DATs so we can get an idea of, what it takes to take these out, document them. Some are cantilevered, some are just wood. Next slide. A mattress up in a tree. Well, I don't think we're going to have a DI for that. Box car, things that storage containers. This one here went over 1,000 feet, lofted, went over a couple of buildings, landed, completely full of equipment. Amazing. Sometimes I just scratch my head and go, yeah, we have some vertical velocities here going on. Unfortunately, the EF scale is pretty much based off of a horizontal flow assumption. So there may be something to be done with these smaller objects that tend to be lofted. We don't have a DI for that though, not yet. Next slide. Missiles, things that go through things. Impressive, but we don't have a DI for that yet. We don't have anything to judge too much. There's some testing done at Texas Tech, throwing missiles at 100 miles an hour. You could do this at 100 miles an hour, but was this attached to anything? We don't know. There's a lot of unknowns here. Next slide. Balled up chain link fences. I've seen tons of these. Really don't know definitively what kind of winds it takes to do this. Look at surrounding damages and say, okay, the house in the background had kind of an EF1 or so. Just depends on how much debris is around, how well attached the chain link fence is, I guess. Next slide. Very bizarre things that happen in tornadoes. We see them all the time. I see new ones every year. Every year I see them. This one on the left, a fence completely got uprooted by the tornado, and this one actually got replanted upside down, this pole. Bizarre. Never seen anything like that before. On the right, some kid's plastic chair was flying around, impacted and penetrated a gable end. The chair is fine. Next slide. And then again, boards and tree branches through things. Maybe stand back, take a look at the building itself and say, okay, how much damage was there to the building? But I have seen boards and branches travel way outside the tornado damage path and hit things. So I'm blocks away from the actual damage of the tornado and I'm seeing boards through things. So there's a lot of lofting going in, which again brings up a huge question about, we know there's vertical velocities in tornadoes. We know that little things get lofted, sometimes great distances. We don't really have a handle on what it takes to do all that yet, and what kind of a DI adjustment needs to be made for that. But anyways, we have other things out there that are very curious to me and us, and we try to get maybe in the future to tackle these things, tackle these issues. And with that, I think we have gone through all the DIs, given you examples. See if there's any questions. My email address is tmarshall@haagglobal.com. That's my company, and I will be there until the end of September when I do retire. Yay! And then you'll have to reach me at timpmarshall@cs.com. So I thank you all for attending. I hope at least it's been somewhat entertaining and educational. Sorry for the big mix-up in the beginning, but I think we got it all straightened out. Thank you,
All right,
Ryan.
Tim. Well, thank you so much. We appreciate that. I know I took away a lot from this presentation. I've reflected on previous damage surveys and your parts about missiles and objects flying. That really made an impression on me because I had a tornado that I surveyed in 2019 up in McCook, and I was just perplexed on what to do because what happened was a big metal grain bin had been lofted and hit the front of the house and totally caved it in. So I was just kind of scratching my head on what do I do here, So thank you for reiterating the considerations and to take in the perspective of the whole picture, not just the fascinating damage that you see, because it may not have been built poorly, or there could be other factors as well.
Yeah, a lot
So,
of bins are not attached very well, some are, some aren't. Grain bins are going to be part of the updated EF scale. They're in there, they pass peer review, so that's a good thing. Irrigation systems are another, which I know those of you out in the plains are going to be happy about. They're going to be in the updated EF scale. We've got great information about irrigation systems and what it takes. The unfortunate things about irrigation systems is that it really doesn't take a whole lot of wind. I mean, there's no such thing, I don't think, as an EF4, EF5 irrigation system. You can't build them that strong, but at least it'll give you some guidance and some a good point of reference.
okay. Okay, Tim, I've got some questions for you that have come into the question box, so I'll go ahead and read them off to you. The
Okay.
first question is it true the NWS generally overrates tornadoes, just in your personal opinion?
Well, I haven't done any kind of statistics to see that. I go out, I do my thing. I know the Weather Service goes out and does these surveys. Sometimes they call me in on things. Sometimes I get an email about questions. So I really can't answer that. I don't have any information to do that. I do see the DATs as they are posted, and my own opinion about it is that what I'm seeing posted done very well. A very good job.
Okay, thank you, Tim. The next question, the first one was from Lauren Nash. This one comes from Todd Kraus. The question is referencing your photo of DI 12, which is the Home Depot. You
Yeah.
mentioned comparing it with the electrical transmission line can help figure out the upper and lower bounds. But what happens if the two DIs don't overlap? Which one should be used?
What I do is I use the worst wind kind of as a default. So if for example I come up with one number with the Home Depot and come up with another number for the ETL that's there, there might be a conflict. There might be such that I'm getting like 120 miles an hour for the Home Depot, and yet the transmission line says it would be damaged at 110 or 100. So you might get those conflicts, and that's part of the, I guess, going out there and doing this analysis. It's still subjective. Sometimes things get damaged and we don't understand why they get damaged so severely when something next to it is not damaged. And it's still perplexing. Fortunately, it doesn't happen often, but it does make us try to rethink whether these wind speeds are correct or not. And we're always open to any kind of suggestions or comments about, but you think that maybe the winds are too high in some of these, maybe they're not. I know that this has been utilized now for almost 20 years, well, actually 15 years. And so far, it seems to be pretty good. I mean, so far, these winds and the damage and everything seem to be doing well. So I'm sure we can get conflicts, and with it, we just have to resolve them best way we can.
Okay. The next question, we are already on the lines of electrical transmission poles. This one seems to be about the wooden power poles. So, will the lower bound be adjusted much from 98 miles per hour? You mentioned it probably didn't take even 98 miles an hour to break or to snap the pole at the ground, given it was rotting. So, are there going to be any adjustments to the new DI for things like this?
Yeah, my answer is yes, especially on poles, transmission lines, freestanding towers. All those in the original EF scale, the 2004 and 2006 versions, there really wasn't much referencing or research done at that time. Now there's been a whole lot more, and I will say yes, they're probably going to come down, especially when a rotted wood pole. We can see those. Doesn't take a 98-mile-an-hour wind to knock those down, even at the lower bounds. So I would say yes, without having to look at the table offhand, given that there's 300 pages written. I would have to go back and take a look, but I would say yes, it's lower than 98.
Okay. The next question comes from Lauren Nash again. Is there any estimate on time when the new DI scale will be done? You mentioned there's a few other things in the works. So any estimate on a time scale of when that will be done?
Now, that's a great question. That's a great question. We have 80 chefs in the kitchen, okay? 80, all right? So it takes a very long time, and I've learned this over the years with a lot of patience, that it takes a whole lot longer to get things done. We're 7 years into this project, and I never thought it would take this long. I would suppose that by putting my best estimate on this thing, there's going to be 3 more years involved with this project. And I'm hoping that there's a 2024 published edition of this standard, and that the Weather Service would adopt it then soon after.
Okay, thank you for that. The next question comes from Jeff Chapman. Is there any attempt to account for debris load with damage indicators?
Great question. Debris loading is a real consideration. You might have to make adjustments to go to more lower bounds if you see that. Some of the issues I've seen in like Tuscaloosa's tornado in 2011, we had some towers go down that were loaded with debris. They literally were caught with lots of debris. And this definitely adds to the failure at a lower wind speed when you have all this debris. I guess in answer to the question, there is no correction factor that we know of, even in the new updated EF scale. It's still kind of your subjective saying, okay, I think debris loading was a problem here on this tower, and I'm going to lower the wind speeds X number of miles an hour.
Okay. The next question comes from Doug Kramer. Any idea what it takes to destroy concrete silos?
Okay, well, concrete silos, depends on what condition they are in. I know in 1970, and I'm dating myself a little bit, the tornadoes went right over a concrete silo in Lubbock, I believe it was Lubbock, and took the tops of them off and did some damage to the upper part of them. And they were in like the 140, 150 mile an hour range, I think, from the going back thinking about that. Knocking down a concrete silo? Well, I'd like to see that. I haven't seen it yet. If there are any photos out there of silos that have been knocked over that are concrete, steel reinforced concrete, we might have to certainly up that wind speed if we find that. We don't have anything like that right now.
Okay, thank you. And just to confirm, another question from Jeff Chapman. Will there be more rule damage indicators? And I believe you said yes earlier in the presentation. Is that correct?
Yes, in fact, we have like 28 of them. There are going to be some combinations in the updated one. For example, small professional buildings and small retail buildings are going to be combined into one. Single wide and double wide mobile homes are going to be combined into one. And so with that, we're adding, I think, about 7 new DIs, and that includes irrigation systems, grain bins, silos. So a lot of those rural areas are going to get a lot of help when it comes to the newer DIs that are out there.
Okay.
If anyone is interested, I have a draft. As long as it's not out there for public at all. This is still a draft, working draft. If you're interested in the draft of the 300-page version, I can send it to you. Just email tmarshall@haagglobal.com. I will send it to you. But it's already changing. I mean, we're having meetings every week, every 2 weeks, and we're updating it, modifying it. Just keep that in mind.
Okay, thank you. Next question comes from Todd Shea. When there are obvious rating errors, even for specific damage spots, do you think it's worth reaching out to the WFO or damage survey team so there is some quality control and consistency within the database?
That's a great question. There's a human factor involved with rating it. When I rate something, somebody else can rate totally different. So I know that happens. It's tough to get consistency across the board because we're all different. So the EF scale, the way it is just like the F scale, it has a range of error. Now, if there's something that's really different, like that that it doesn't take a 200-mile-an-hour wind to do this, it only took a 100-mile-an-hour wind to do something. Yeah, certainly if there's that kind of disparity, I'd bring it up, talk about it with somebody. Most of the time, the EF scale has this error of about plus or minus 20%. You can go into one or more EF numbers. You can say something is EF3 when it's EF2 or something is EF4. It could be that dramatic in some instances. So yeah, discussion is always good as long as it's a friendly discussion.
Yes, I agree. The next question comes from Paul Howerton. I'm not sure of this acronym, but is there any thought to adding ICF homes or buildings as a damage indicator?
Insulated concrete forms, yes. And in fact, one of the new DIs that's going to be coming out in the future is on concrete block stucco homes. Now, although we don't have ICF in there, and the reason being is ICFs are still rare to find, and so we are not going to have a DI for them, but we will have a DI for concrete block stucco homes, which are pretty common in Florida, southeast, southwest, in fact, as well. So you'll have some guidance in that range. ICFs, I will say, are extremely strong. I have had the opportunity to look at a couple of steel reinforced concrete dome homes up in Oklahoma that the damage on either side of this home was EF5, and these homes survived, although one of them had a cracked shell, a freshly cracked shell, windows blown out, of course. But the occupants, who were literally sitting at the kitchen table when the tornado hit, because they couldn't hear it, they were fine. So it's just, they went right through the middle of an EF5 tornado in a concrete dome home. So I will say that they're virtually indestructible. if I may. And I know homes in Guam, for example, they have a lot of homes that are built of concrete there, including the roof. And they do quite fine in the typhoons there. So it's going to take a lot more wind in order to knock one of those down.
Okay, thank you. The next question, it's actually from two people, Todd Kraus and Brooke Hagenoff. They seem to be on the same wavelength today. So the basic question is, what are your thoughts on, you know, 3-second gusts versus slow-moving tornadoes, or residence time of the tornado over one spot, 1 minute versus 10 minutes, and something along the lines of like a Gerald, Texas tornado. So, what are your thoughts on the residence time of a tornado in a certain place or certain spot, and the damage that results as a result of a longer residence time?
Yeah, another excellent question. Duration factor here. Yes, this goes right along with the debris loading. It's like, having surveyed Gerald and calculating that tornado took 3 minutes to go over a point if you were in the center. 3 minutes is a long time in a tornado, and certainly does a lot more damage than when it's there and gone in seconds. So we don't have a handle yet on what it would take or what factor to use, because a lot of stuff that goes into the standard that we're talking about has got to be based on peer-reviewed stuff. We don't have enough material to go and do that. Now, some of the numerical modelers are helping out with that, but I don't think we're all there yet. So it's an excellent question. Certainly makes a difference how long a tornado is over your house. Duration factor is key. Debris loading is another one. Those are great questions, great issues. Maybe a future iteration of the EF scale will be able to get a handle of it.
Maybe the EEF scale. So,
Yeah, we've
okay,
batted that around. Is this the enhanced Fujita scale? Yes, that's what it is. It's the enhanced Fujita scale.
okay. All right, our final question of the day, and we'll let you off on the hook with this one. It comes from Ed Shimon. Is there a wind rating for the lifting of sections of blacktop road?
Another great question. Blacktops are, of course, various qualities, various substrates. We've seen many blacktops get lifted by tornadoes and removed. We don't have anything, again, peer-reviewed wise that we can rely upon. We've seen it. We think it takes a pretty high level wind to do that, something in the neighborhood of 150 to 200 to do that. So that's up in the EF upper 3s and 4s and 5s to strip off pavement. But again, it's more like looking around and seeing what other damage there is. We are having in the next iteration of the EF scale, the highway beams, the concrete beams that you see go up on these highways. We've got enough information to tell us what it takes to knock those over. So that's going to help in the highway, in rural areas, on an interstate. Got these concrete sections that are a couple feet high, 10 to 20 feet long. We know what wind it's going to take to knock those over. I myself have been very interested in parking curbs. I've seen several parking curbs, concrete ones, lifted and thrown, but still we don't have enough information about that to include it as a DI. So, like I say, long after I'm gone, it's going to be up to the next person to try to enhance the enhanced Fujita scale, make it another E on it.
Awesome. Well, Tim, I'm going to go ahead and let you off the hook for questions. I just want to thank you again on behalf of all of us for being willing to take time to talk to us about this. Obviously we're meteorologists by trade, so the engineering doesn't come naturally to us. So thank you for showing us like what to look for, the differences between well built and poorly built. We really appreciate that. And we also want to wish you the best in your upcoming retirement. That's going to be a big loss for the weather industry. And so thank you again for taking time to impart some of that knowledge upon us. So thank you for that. And with that,